Okay, so to prepare for writing out ELF files, I've got two PDFs here. One is the gABI ELF PDF, which is the ELF object file format specification version 4.2. And then I've got this psABI for x86-64, which is the processor supplement for AMD 64. I'll only be focusing on 64-bit output for this because I'm writing 64-bit machine code on 64-bit machines, so I'll just completely ignore anything relating to 32-bit here. So I thought the first thing I should do is basically collect together all of the types and structures from the ELF spec, and that I will most likely need. And then next time I can actually get into representing relocatable object files in memory and writing them out to disk for passing to existing linkers like LD, LLD, stuff like that. On Windows, if I do COFF files, it would be link.exe, for example. So going through the ELF spec here, basically, there are three types of object files: executable file and shared object file. I will not be writing. I'll only be writing relocatable files to pass to existing linkers, or static linkers, link editors, whatever you want to call them. And here's just like a simple diagram of the layout of an ELF file. The only real requirement is that the ELF header has to start at offset 0, because then this points to where everything else is anyway. So the only difference here is that in a linking view, the section header table is required, so I'll definitely be outputting this, whereas the program header table is optional. And then in the execution view, the program header table is required, but the section header table is optional. So looking at these data types here, we've got ELF32 prefixing the 32-bit versions of types and ELF64 prefixing the 64-bit versions. So I think I'll just start by taking these, and unsigned char here I'll just use as byte in Go, so I won't bother with that. So what we can do here is create like an object package where we have ELF. And at a later time, I'll probably have a COFF in here as well. So we'll have elf.go package ELF, and we'll start with these sort of like base types here. So an address in 64-bit is 64 bits, so this is uint. The ones that begin with S are signed, and all of the other ones are unsigned. So an offset here is also 64-bit. Half is half of a word, which is 32 bits, so this is 16 bits. This one will be 32 bits, this one will be 32, but it's int32 because it's signed. This one is 64 bits because it's an extended word. And then this one is the same thing but signed, so this is int64. So we'll just check this. This is 264, so this is 8, 8, 16, 32, 32, and then we've got 64, 64, and then for this one I'm just going to use bytes, so I can ignore that one. So if we go to, also it says here that, for example, I just want to point out that it says the data structures that the object file format defines follow the natural size and alignment guidelines for the relevant class. If necessary, data structures contain explicit padding to ensure 8-byte alignment for 8-byte objects, 4-byte alignment for 4-byte objects, and so on. So I will create like, I will align these things on disk. I don't have to pay attention to alignment for stuff that will just be going into like memory somewhere, but there's no harm in just aligning it to what I say the alignment should be for memory, so I'll just do that on disk as well. So if we go down a bit further, we get to the ELF header. So the ELF header is the only thing that's sort of required to be at offset 0, and we've got a 32-bit version and a 64-bit version. And then we've got this const here for EIN ident, which is basically just creating this 16-byte array down here. So we'll take this n-ident const first. Let's just do, maybe we'll put const up at the top here. So this is 16. Then we just need the 64-bit ELF header struct, which I guess I can't copy easily, so we'll just type this out. So we've got, this is called elf64 elf header, which is a struct. So we have ident, which is a EIN ident of bytes. So this is a 16 byte array. Then we've got type machine version. So let's just put these on separate lines here. Then we've got entry, ph off and sh off. So this is the program header offset into the on disk from the beginning, and then this is the section header offset from the beginning of the file. Then we've got flags, and then down here we've got EH size, which is the elf header size. Then we've got ph ent size. So this is the program header entry size. And then we've got ph num, so how many program headers are there. Then we've got the same thing for section header. And then finally we've got the section header string index. So all of these ones are half. Then from the top we've got two that are also half. We've got word adder and then two offsets. And then flags is just word. Okay, so that's the elf64 header. I'll then need to take these consts as well, although I think I'll only really be using this one, but I'll just copy them all over anyway. So let's just put these on the correct lines. Then we've got versions, so we'll just define these. So this one is none is 0, and then this is 1. Machine here makes a reference to this appendix A, so we'll just go down to appendix A quickly. For this one, I will just take the relevant machine, which will be x86-64, so this is defined as 62. So let's just go back up to the elf header. Okay, so then we've got version, entry. I can't see any of the links here. Okay, that's all fine. Okay, so now these constants are basically indices into the ident array. Put these here. I already have n ident, so maybe I'll just get rid of it from the top here. Okay, so these are for the magic number, so we'll just put these in down here. Let's get rid of these quotes. These should be runes, so we'll just do that. That will allow me to put them as bytes. Then we've got the class. I'll take all of these, even though I'll just be doing 64. So we've got 0, 1, and 2. Then we've got the data. So I'll be using LSB for this. So we'll just go to here. And this is actually defined in the psABI. It specifically says use LSB for the x64 ABI. Okay, so this is just describing the what the indices mean. This is just a diagram of LSB versus MSB. So it's basically little endian versus big endian. So now sections. Let's just see what we need in here. So this is a section index. We'll just take all of these out of here. And match these up with the correct ones. So then we just got a description of them. Okay, so section header table entry. I do need this because this is going to be what describes where each of these sections are. So let's just take this down here. So this is going to be type, and we'll move the name up to here. Let's just take, okay, that one needs to go on the same line there. Take all of these and put them at the beginning. Okay. Looks like that's about it for there. So section type, I won't be using most of these, but we'll just take them all anyway. Put them below here. So then we just got a description of what all of these are. Okay, so now section flags. These are going to be needed as well. So we'll just take these. Okay, I won't get into what any of this stuff really means because I think I'll just describe it as I'm actually representing these things in memory next time. So this is just a description of what to set the link and info fields to based on the type of the section header. So we'll just skip that for now. That will be more for next time. Yeah, the first section header table entry has to be a 0 value. Same goes for like string tables. There's a null byte at the beginning. So it just means that if you have like undefined things, then they can just sort of like automatically point to the null entry. I'm not going to be doing anything with compressed sections, so we'll just skip that. Don't really care about rules for linking unrecognized sections right now. Section groups I can skip at the moment. This is just sort of like if you're gonna, it's just telling you what to set things to basically. So if you're doing like a text section, then you want to set the type to prog bits, and then you want to set the attributes to the bitwise OR of alloc and exec insta. And then a bit more description about each of the section types here. So we'll just skip over that stuff for now. Okay, so string table, string table is basically just a byte slice, really. So I'll leave that for next time. I don't think there's anything that special about this. Okay, so symbol table. So let's have symbol table index undefined. This is 0. And then we do need the structs for this. So symbol table is basically, you know, if you have like labels and stuff, then you can put it into the symbol table to do things like resolving addresses and things like that. So let's just take this. We'll do unsigned char is byte. Let's just put this on the correct line. And then we'll just take all of these. Take all of these, put them on the beginning. And capitalize them. Okay, so st_info, this is basically like a packed, it's like a packed value telling you what the bind and the type of the symbol is. So I'll take these ELF64 ones and just turn them into functions. So let's just put these on these lines. So if this is info, then it should be bytes. We'll just return a byte. Don't need these parentheses here. Define can just turn into function. I don't think I need any of these parentheses actually, so this should just be t. Yeah, okay, that's all fine, that groups correctly. Visibility, probably don't really need this, this as a function, but I'll take it anyway. So visibility here is actually going to be, is it going to be info? I can't remember. Let's just have a look at the struct. Oh, this was other. Yeah, okay, so other is this one here, which is also a byte. So let's actually just take byte for this as well. So B is bind and type is, T is type. This will also be bytes, and this one will also be bytes. Let's just get rid of these needless parentheses. We'll take byte for this as well. Don't need anything else there. Okay, so this is like the binding. So local being local to the object file, global and weak meaning that they can be sort of seen outside of the object file for resolving like relocations and stuff. Is there visibility as well? I think there's visibility and stuff down here. Okay, so this is, these are going to be more constants, so we'll put these up here. So we've got 0, 1, 2. Then we've got 10, 12, 13, and 15. Okay, so then we've got symbol type. So let's just take all of these. Symbol visibility is like where can it be seen outside of the component that it's a part of? So a component being like an executable or a shared object file. Okay, let's just go on to these other ones here. No more constants here. I will need a structure for relocations, and I will be using this rel A1, so it has the explicit addend in it. So we've got E header section, so this is elf header, section header, symbol, and relocation. I think that's actually all of the structures that I'm going to need. So let's just get this set up. Okay, and then we've got a few defines here to help with packing information into the info field. So this is the, I guess this is the symbol index, I think, and then this is the type of relocation. And types of relocation are processor specific, so those will be in the psABI PDF. Okay, so if this is for info, then that's going to be xword in this case. So we'll do xword, and it can return xword. I need to get rid of these L's on the end. Okay. All right, let's just get rid of these pointless parentheses, at least for Go. So we've got T here. That one can come out. Okay. All right, I think that's okay. And then it moves on to program loading, which is more just for like how to load a program into memory and do the dynamic linking and stuff like that. So I think that's everything that I'm going to need from this generic ABI here. Maybe we'll go and have a look at so we've got machine values. OS ABI, I think I'm just going to be sticking with none. I think I'll need to take these though. So let's just put these in the constants here. This 0 should go up to here. Okay, I think that's everything I need from this document right now. So let's just move on to the psABI. So if we go to object files here, so it tells you a bunch of stuff about, you know, if you're doing a 64-bit, then you want ELF class 64, and you want LSB to be the data encoding. Tells you the machine identifier to use, etc. Section flags. We may take this one. Let's just put this one into here. Section types, I suppose we may as well take this one. Not sure if I'll be using it, but... okay, so there's a bunch of just special sections here for global offset table, procedure linkage table, and I think this is like, yeah, this is related to unwinding. Okay, so let's just skip over all of this stuff now. This is more about stuff that I'm not interested in right now. Symbol table, yeah, we'll just skip over this stuff right now. Okay, so relocation types is the next thing that I'm interested in. So let's just take all of these. Okay, if we just go down to here and copy these, I'll mostly be using PLT32, PC32, and maybe like a global offset table PCRel. There is a PCRel X, I think, in here as well, which allows the linker to relax things. Oh yeah, here it is. There's relx and then relx. These ones actually sort of allow it to rewrite the instruction a bit, I think. Some of these are just in here. I think it says somewhere in here that they're in here for more like documentation purposes rather than being sort of like conformant to the ABI. So for example, PC8 is in here, but probably best to not use it. But I'll copy all of these in anyway. So we'll just take all of these and put them over here. Let's just line up these numbers correctly. Let's go up to the top here. There's actually two deprecated ones here, so I'll get rid of those, and we'll get rid of these symbols. Okay. All right, so that's all of the relocation types. I don't think there's anything else that I need to take from here. Relocation, okay, I mean, I'm not really going to be doing large model stuff right now, so I'll just skip over that stuff there. And then this is just now about dynamic linking and program loading and stuff, so I think I'll just stop here. I think I have enough now in this ELF file to sort of like represent all of the data that I'm going to want to write to disk. I think maybe for the final thing is that I know that I'm going to have this file thing. So this will be like representing the file in memory before I write it out. So it's just I said earlier that the ELF structures should be aligned on disk. So I'll just have this aligned helper quickly. So we'll say, for example, if we've got I and then align, we'll just do int for now. Maybe we'll change it from int a bit later. So because this is always a power of 2, we can just do this this sort of special way of doing it where we just do I plus align minus 1. and then we'll basically just unset, or we'll do AND with the inverse of align -1. Okay, so I guess OBS stopped. So back to this example anyway. So we've got, if we pass in, for example, 6 here as the thing that we want to align, we expect this to go up to 8 if we pass 8 in as the align value. And we'll only allow powers of 2 in align, which is why this bit trick is going to work. So if we just do the maths here, basically we've got 6 plus 8 minus 1, which is 13. 12, I think in binary was 1, 1, 0, 0. So if we add 1 to that, we get 13. Then obviously, because this is an int, we've got a bunch of zeros on the beginning here until it fills up to 64 bits or whatever. Then for the align, we're basically going to take a line which is 8 and -1 to make it 7. So it changes from 1, 0, 0, 0 into being, a bunch of zeros. It would normally be 1, 0, 0, 0 for 8, but then the -1 is basically turning it into 7. Then if we take the inverse of this, it changes all of these into 1s, and it changes these bottom 3 into 0s. So we've basically just extended this this bit in the 8 position all the way up into the sort of leading 0s there. So if we basically AND this with this, the align of 8 with this bit trick here has basically set the granularity for the I that we want to align. So if we AND these two together, we'll end up with these zeros still. The bottom 3 zeros are going to be zeroed out, so we're going to end up with 1 in the 8's place and then 3 zeros here. So we've basically ended up aligning 6 up to 8. Which is correct for this case. So this works as a nice trick to use for aligning a number as long as the align is a power of 2, because then you can do this binary thing here. So anyway, that's just, I thought I may as well put that in now before I get to the next actual implementation of things.